Okay. Let's continue from where we left. So before that, we just touched upon the PROMs, PALs, and PLAs. So I just checked the contents that I have. Those particular contents are there in my office actually. So in case the campus opens and if I am able to go to my office, we will cover those particular material. Else we will skip that particular portion. But however, I'll touch upon the problem so that you know anytime you study computer architecture, you could just recall that this is how your memories are working, whether it may be a RAM or it may be a ROM. This is how your memories are working with regarding to the digital electronics is concerned. So just for your sake of understanding, but otherwise this will not be a part of your topic. If we cover in the lecture, then that will be in your topic, but it depends whether the campus opens or not. Okay. All right. So what we were doing in the Okay. So we were doing counters, right? So we were just designing how to design a ripple counter. Ripple counter means what? That is the output of one flip-flop is fed as a clock to the input of the next flip-flop. In this particular example, you see, so this is a 3-bit binary flip-flop. So the number of bits, there are 3, it is a 3-bit binary flip-flop in the sense you are going to count from 000 to 111, which means you will require 3 flip-flops. So the output of your flip-flop 0 will be fed to the input of a clock of your next flip-flop. And you must note here that we are using the output of the negative complement output of each flip-flop, right? So negative complement of each flip-flop. So only if you operate in the negative complement of each flip-flop, then they corresponds to the rising edge clock of rising edge clock. So you will have a positive triggered flip-flops. These are called as positive triggered flip-flops. Now we will see, I think we touched upon the negative triggered flip-flops also. What is the negative triggered flip-flop? Is instead of you giving the outputs from the complement outputs, you give the inputs from the positive logic. So if you are giving an output from the input from the positive logic, then what happens is, I think we touched upon this also. Yes. Let us consider another example of a 4-bit triple binary counter. This is negative edge triggered. What do you mean by negative edge triggered is, unlike the previous case where you connected your Q0 output to the clock here, Q0 bar output to the clock here, you are connecting Q0 output to the clock. In this particular case, every time you are having a falling edge of your clock. Falling edge of the clock means from 1 to 0. From 1 to 0, you will have the next flip-flop getting triggered. Okay, so let us look at the timing diagram here. So this is the clock. Okay, so this input is your clock input. And we see that since this is a negative edge triggered clock, negative edge triggered means 1 to 0 transitions, your clock pulses will be effective. So here we are having a 1-0 transition. Here we are having a 1-0 transition, right? During these falling edge clock pulses, you will get your clocks getting triggered. So whenever you have a negative edge triggered clock, you see here that your Q0 output, the first is your Q0 output, right? Whenever you are having a clock here, the output that you will get will be this Q0. Only this negative edge triggers this particular output. Likewise, for the next 3 flip-flops. So whenever you are having a falling edge clock, you will get your Q0 output going high. And whenever your Q0 output goes from 1 to 0, then you will have your Q1 going to high. So let us see here. So whenever your clock, rising edge clock goes from 1 to 0 here, your Q0 goes to high. And whenever your Q0 goes from 1 to 0, because this is a falling edge clock, your Q1 goes to from 0 to 1. Whenever your Q1, and this will continue to stay till the next transition. When is the next transition taking place? Your next transition is taking place only here. Here you are having a 1-0 transition here. So during this transition, this Q1 again will be triggered from 1 to 0. So here you are having a 1-0 transition, which will further trigger your Q2 output here. Okay, again, whenever this Q2 is going from 1 to 0, and when will this go from 1 to 0? Only when your Q1 is getting another transition from 1 to 0. So this is getting another transition from 1 to 0 here. So your Q2 will also be triggered. So now this is how the timing diagram will work. Now let us verify whether our counting sequence is working or not. So let us count our sequence now. We need Q3, Q2, Q1 and Q0, right? So Q0 is our LSB bit. So it is 0 MSB. So Q3 is our MSB bit. So your Q3 is 0, 0, 0. Before this, it is 0, 0, 0, 0, right? So we are starting from 0, 0, 0, 0. Then it is 0, 0, 0, 1. Then it is 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0. Likewise, and then here it is 1, 0, 0, 1, 0, 0, 1, and finally it is 1, 1, 1, 1. So we have the counting sequence here for negative triggered flip-flops also. So it depends whether you want to use a positive edge triggered or negative edge triggered flip-flops. Both are fine. Okay, so all this, whatever we have seen, they are all synchronous flip-flops. Synchronous flip-flops in the sense, if you have a 3 flip-flop based on the clock, because all the clocks are fed here in a rippled fashion. If you have 3 flip-flops, then it will start counting from 0 to 7. You have 4 flip-flops, it will start counting from 0 to 15. If you have 5 flip-flops, you will start counting from 0 to 31. But what if you want to count only till 10? What if you want to count only till 18? What if you want to count only till 26? Then what we do is we go in for an asynchronous flip-flops. Now, using this particular structure, right? This is a 3-bit ripple counter, right? Can you count till just 5 using the same configuration, right? We have already seen enough examples in our tutorials. I want to have only a counter counting from 0 to 5 only. I have to use the same ripple counter. Then what do I do? What do you do is, after a count sequence of 5, you reset all the flip-flops, right? That is what is called as an asynchronous flip-flop is. Asynchronous counter is, right? How do you do that? Whenever you want to count only till 5, and whenever you are counting 6, it must reset. That's the logic, right? So when will you have 6? 6 corresponds to 1, 1, 0, which means that your Q2 is 1 and Q1 is 1 and Q0 will be 0. Okay, so this should be like this for the sake of convenience. Yeah, I add all these things. In fact, I NAND this and then connect it to all the preset input here, all the preset inputs. Now this will be reset whenever your flip-flop reaches 110. So this is the asynchronous way of having a counter for any other number other than these counters. So let us look at how to implement. Now we are going to see an asynchronous counter with mod number less than 2 power n. Whatever we have seen so far is 2 power n. Example, say I want to count till mod 17 only. So how many flip-flops I will require? I will require 5 flip-flops, which means that 32 different counting, 32 states are possible, 32 counting sequences are possible. But I want to only 17 and I want to skip the rest of the thing. So here the rest of the states can be truncated in the sense once you reach 18, you can reset the flip-flop. Okay, so this is the logic we are going to use for an asynchronous counter with mod n less than 2 power n. So the same logic that I just said. Yeah, so this is an example here. This is a mod 6 counter. This example here is a mod 6 counter. Why mod 6 counter? Now, otherwise it counts sequentially. So this has been done reverse. Okay, see here, every time we have been giving inputs from the left hand side, here the inputs are given in the right hand side. So which means this will be LSB and this will be MSB, just for the sake of visualization. Okay, so Q is fed to a JK flip-flop, which means that what kind of flip-flop is this? This is a positive triggered or negative triggered flip-flop. These are negative triggered flip-flops. Why negative triggered flip-flops? Because we are giving from Q instead of Q bar. If we are giving from Q bar, then it will be a positive triggered flip-flop. Okay, so this is a negative triggered flip-flop and this is a mod 6 counter. How did I presume that this is a mod 6 counter? You see here, what are the inputs I am getting here? I am getting the inputs from Q2. This is Q2, right? I'm not getting any input from Q0 and Q3. So my Q0, my Q, oh, let me write it as Q1, this one. Okay. So my Q1, Q2 and Q3, they are having 1, 1, 0. I'm not bothered about the 0. So 1, and whenever I'm having both inputs 1, I'm clearing all the inputs. See here that all my inputs, all my flip-flops are cleared by this particular trigger. So I'm forcing a reset here. I'm forcing a reset here whenever I'm having 2 1s here. Otherwise, since this is a 3 flip-flop, 3 flip-flops, if you look at the truth table or input combination 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1, which means that these two are not required states. So that is the reason I did not connect 0 to this. I did not connect this Q bar to this, because whenever both the inputs are 1, I can just reset it, right? By this way, I have to use only 2 input NAND gate. Otherwise, if I want to connect Q bar also, then I will be using a 3 input NAND gate, which will be slightly costlier. Okay, so hence we are forcing a reset here for a mod 6 counter. So hence these are called as an asynchronous flip-flops with less than 2 power n mod numbers. Okay, so this is the timing diagram that takes place. Maybe I'll quickly touch upon the timing diagram also. This is a negative edge triggered flip-flop because we have been connecting Q to the next clock. So hence negative triggered likewise. Now what happens? There is a counting sequence. So whenever there is a negative sequence across Q0, then there is a transition taking place, right? So negative transition, there is a transition taking place. So initially it counts from 0 0 0 0 0 1. So 1 0 1. When we have 1 1 0, then your flip-flop must be reset here. You are having 1 1 0. If you don't have this NAND circuit, this is how your input sequence will keep on continuing. Please see here, ideally without a NAND circuit, this is what this will continue. But since we have connected a NAND circuit and we are clearing our inputs, our NAND operation, you see here that whenever it is 1 1 0, it is 1 1, in fact, you are resetting it. You are giving it to a NAND here. Whenever your input is 1 and 1, your B input, right, it actually rises, right? So your B input here has been copied here only till this particular point. Your B is rising here, and at the same time your C is at this particular position. Look at where is B and C here. Once you have your NAND gets detected this 1 and 1, then what happens is it is clearing all the flip-flops here. So your NAND output This is your NAND gate output. Normally it is 0. Whenever it detects 1 and 1 here, it gives you a high here. When it gives you a high here, it clears all the flip-flops. So which means B, when it is high, it gets cleared and it comes back to 0. It is 1 here, again it is cleared and it comes back to 0. We have connected it to A also, right? So A also, let me draw here. So A is also, it is transitioning from 1 to 0 and it will continue to be 0 here. It is transitioning from 1 to 0 here. And since we are resetting it, it will continue to be 0. Okay, so this is how we are resetting our mod 6 flip-flop. So what we do here is your mod 6 counter is produced by clearing when count of 6110 occurs. Okay. So any doubt here? Okay. Next, let us move. Let's say, for example, you are given a counter circuit. How do you identify that what kind of a counter is it? Okay. So my question here is, say this is a counter. Okay. This is a circuit. This is a counter circuit, some mod counter circuit. On looking at the circuit, can you answer me the following question? First question is it a positive triggered circuit or a negative triggered circuit? My second question is, what is the mod n value of this particular counter? Can anybody answer my first question? Whether it is positive triggered or negative triggered? Is it positive triggered or negative triggered? I will wait till you swallow your food. No answer. Sleeping. 57 of you no answer. Not even from a single person. Nobody. At least towards the end of the semester, you can answer. Okay, fine. So what are the outputs here? How many outputs? First, what is the maximum mod counting that you can do? A, B, C, D, E, F. So it is still F. Maximum counting that you can do is okay. I got some answer. Why did they leave the class? They are coming only now. Okay. All right. So what is the maximum counting sequence that I can have? A, B, C, D, E, F. So 1, 2, 3, 4, 5, 6. Right. So this is the maximum counting sequence I can have. But at the same time, I'm resetting. When am I resetting? Whenever I'm getting the C output is connected here, D output is connected here. So let me assume that this is F, E, D, C, B, and A, B, C, D, E, F. So whenever I'm getting C, D, E, F to be 1, 1, 2, 3, 4, 0, 0, I will reset. So what is this particular value? This value corresponds to, A corresponds to what? 2 power 0. I should write here. A corresponds to 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, and 2 power 5. Okay, so this corresponds to 1, 2, 4, 4, 8, 16, and 32. So I have, what will be the counter? It is 32 plus the 1 here, so 16 plus 8 here plus 4 here. So this counter will be 32 plus 16 is 42, 48, 56, 56 plus 4, I think 60. It is a mod 60 counter. Let us see whether am I right or wrong. Yes. So it is a mod 60 counter. So what does this mean is, on looking at the counter, you must be able to tell what kind of counter is this particular circuit is. Okay. All right. So maybe you can design something like an asynchronous mod 5 counter. So what will be the logic? Whenever you get 110, you will reset it. It is mod 5 counter only, right? You have to count till 5. And when 6, you have to reset it. Mod 7, whenever you get, so you have to count till 7. Okay, so you do not want to have any reset circuit for this. Okay, mod 12 counter. So these are the counters. Okay. So when A and C are 1, you can reset. When all 3 are 1, you can reset. For mod 12, this is A, B, C and D. When C and D are equal to 1, you can reset. So this is the simple logic by which you can have these counters. Now let us move on to a decade counter, or in fact, the other name of a decade counter is a ripple counter. The other name of a BCD ripple counter. Why BCD ripple counter is because we count till 0 to 9. So how many states are here? There are 10 different states. 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. So 10 different states are there. Hence, these kind of counters are called as ripple counters, or the other name is called as a mod 10 counter. Now, how do you implement this? Number one, we have to decide how many flip-flops you will require. If you need to count till 10, then you will require 4 flip-flops, and the unused states will be 10, 11, 12, 13, 14, 15. These are the unused states. So whenever we reach 1001, which means 9, and whenever we reach 1100, we have to reset. We have to count till 9, and then at 10 we have to reset. Okay, so that is the logic. So yeah, the state diagram is also this way. You start from 0, you count till 1, 2, 3, 4, and then 5, 6, 7, 8, 9, and see here, 0 to 9 you will count, and 1010 you will reset, which means that if this is, let me write it, A, B, C and D inputs, whenever my B input and D input are high, I will connect it to a NAND gate, and then I will clear all the 4 flip-flops. This is the simple logic. Okay. All right. So, but the problem here is, you have to first completely look at the truth table. Is only at these particular positions are you get both 1 and 1. Now let us see how to design such a kind of a decade counters. So yeah, this is another way that has been taken, never mind. So all these are JK flip-flops. All these are JK flip-flops, right? All these you can see that they are shorted, and then they are just shorted. They are not given 1. So now we give a clock to the first flip-flop, and the next clock is triggered from Q. So which means that these are positive triggered flip-flops. So we are having a NAND gate, so which means that the input to our NAND gate, so this is your Q4. Okay, you see here there is a slight change in the notation here. These are, we are naming it as a decade counter. Decade means 10, and at the same time we are expressing these output of our flip-flops as decade powered, so as Q1, Q2, Q4 and Q8. So we are taking outputs from Q4, and the other output is coming from Q2, right? So whenever these two are once, we are resetting. No, we are giving this to our J. There seems to be some mistake here. Okay, so let me. Yeah, I think the logic is right. Yeah. Yeah, I think this particular circuit seems to be, there seems to be a mistake here. Okay, so your J and K here is shorted, and then there's been a okay, I think this has been taken straightforward from the BCD counter, right? So we'll come back to this later. So the logic here is whenever we get 1001, we are counting from 1001, and then after the 10th clock 1010, we reset our state, right? So which means that Q8 and Q2, whenever they are 1, then we reset it. That is the simple logic we use. We will come back to this decade counter later. What is this particular design about? This particular circuit seems slightly different, so I will have to relook at it. Now, okay. So what are the things that you need to note here is it is a negative edge triggered flip-flop. If you want a negative edge triggered flip-flop, then you connect your Q to your clock. If you want a positive edge triggered flip-flop, then you connect your Q bar to your clock, and that will be, sorry, you connect your Q bar to your clock, and when you are doing so, the counting that you are performing is an up counting. If you want to perform a down counting, and if you want a negative edge triggered flip-flop, then your Q bar must be connected to the clock. You want a positive triggered flip-flop and you want a down counting, connect your Q to your clock. Okay, so this is one important note. Second important note is you can cascade your counters. How you can cascade your counter is, say for example, you want a mod mn counter, meaning I want a mod 6 counter, let us assume. Okay, then I can have two counters. One is mod 2 counter and other is mod 3 counter. Mod 2 counter will count from 0 to 2 and mod 3 counter will count from 0 to 3. These two counters, mod 2 and mod 3, can be cascaded together. That is what is called as a mod mn counters are. So now let us see how to cascade it. Yes, this is how your decade counters are cascaded. Let us assume that we are having one BCD counter. Please remember that we will be resetting after whenever we get 1010. Okay, because 1001 we will be counting. So how do we cascade this? So which means let us assume that we are having three BCD cascade counter. So one BCD counter will count from 0 to 9. Second BCD counter will also count from 0 to 9. And third BCD counter will also count from 0 to 9. If we have these three counters, then the maximum counting that we can do is till 999. That's the logic. So how do we do that is, let us assume the first BCD counter which can count from 0 to 9. Am I right? 0 to 9 can be represented as a 10 per the zeros digit or the ones digit. Then the tens digit. So these are ones digits, these are tens digit, and these are hundreds digits. So by cascading this counter can count from 0 to 9. This counter can count from 10 to 90. Combining this, I can count from how much? 0 to 99. This counter can count in terms of hundreds, 100 to 900. So cascading this, I can count from starting from here 0 to 999. I can count. Okay, so this is how we cascade the BCD counters. Let us take an alternate there is a simple design also. Say for example, what if you want to count only till 399 instead of 400? Okay. So we follow the same thing. We reset it. For instance, you want to count after 399. The count after 399 will be 400, and you want to reset it. How do you do that? Or another simple design of a we will mod 10 counter is. This is one example, right? I said that we will come back to this particular circuit later. What is this ripple counter? This is the circuit that I was telling you, that you connect your A and B, that is 1010, you have to reset. So 1 corresponds to A input and C corresponds to another 1 input. So this is coming from Q0, or you can write it as A. This is A and this is C. The output of your C is coming here, and then you reset and you clear the flip-flop. This is the simplest logic you can implement for a BCD counter. Okay. Okay. Now, so this particular cascading that we have seen, this is for decade counters in the sense you will not have any control if you want to count only till say 500. In such a kind of a counter where there is no reset signal, then you will count to the maximum counting sequence. So what is the maximum counting sequence possible for this counter? It is starting from 0 till 999 is the maximum counting sequence. Once you have the counting clock pulses, it will count till 0999. If you want to count till 500, then you have to do a reset operation here. Now let us see how to design an asynchronous counter, but for cascading. So let us say, for example, you want to design mod 32 ripple counter. I said that mod 32, this has to be in the power of 2 only. So I can either have a mod 2 counter, or I can have a mod 4 counter, or mod 8, or mod 16, or mod 32 counters, etc. If I want a 32 counter, what combination can make it as a 32? Only 4 into 8 can make it as 32. So I can cascade, and it is clearly given in the problem that you have to use mod 4 and mod 8 counters only. So 32 can be written as 2 power 5. So 2 power 5 can be written as 2 power 2 and 2 power 4. And 2 power 2 is nothing but 4 flip-flops, and 2 power 3 is nothing but, 4 counting sequence, and 2 power 3 is nothing but 8 counting sequence. So I will, let us see how many flip-flops I will require. I will be needing 2 flip-flops for a mod 4 counter, 3 flip-flops for a mod 8 counter. Am I right? So total, I will be needing 5 flip-flops to have a mod 32 counter. So what is the logic here is, this is the first 2 will be your mod 4 counter. So I am giving a clock pulse here. This is your Q0 and Q1. This is a positive edge triggered clock. All these are positive edge triggered clock. Okay. And this particular block will be a mod 4 counter, and this particular block will be a mod 8 counter. So I can cascade it. But it looks like a mod 32 counter in a single core, right? But you have to look that this is one single IC with some pins, mod 4 counter, and this is another IC with mod 8 counter, which means it will have 3 flip-flops inside this, all 3 flip-flops, and this will have 2 flip-flops inside this. So we can just connect this Q bar output of one of the flip-flop to this, and then you can use it as a mod 32 counter. So you need not look at mod 32 counter as just as a flip-flop, but you have to visualize this as one single IC, one containing 2 flip-flops of which is a mod 4 counter, and another IC with mod 8 counter, right? Okay, any doubts till this? I'll just quickly summarize because before we move on to any other type of counters. Okay, we started with the binary counters. These are called as a ripple binary counter, and with these binary counters you can count only till the maximum mod numbers. If 3 flip-flops, then you can count till 8. But what if we want to count to any number less than the actual 2 power n number of mod numbers? Then you have to reset accordingly. So we took example of resetting it. So using these NAND gates based on the outputs where we want to reset, we can use these NAND gates. Then we saw cascade counters, right? So the cascade counters are normally designed with the help of a BCD counter. Cascade means decade means decade. It's actually zero. Decade means it is 10, 100, 1000, 10,000 likewise. So decade counters. We will be using only BCD ripple counter for that. Why BCD ripple counter? Because only in BCD ripple counter we can count from 0 to 9. We have already designed a BCD ripple counter in the previous class. We can use that particular counter. There are two ways by which you can design. Either you can use this particular logic or you can use resetting the logic. That is this particular one. You can resetting this logic. All you need to look at is each one is a BCD ripple counter. So the complete thing will come as a single IC. So all these decade counters you can count only till the maximum count value again. If you have 3 counters like this, you can count from 0 to 999. You want to count 0 to say 200 or something, then you have to again reset this. That is what we are seeing now. What about cascading an asynchronous counter? So as an example, we have taken this at mod 32 counter, we are using it. Next, another kind of an asynchronous counter is called as a ring counter. Now, basically these kind of ring counters, we will be using registers. Registers in the sense we will use D flip-flop. Okay. Please remember that when designing this, you can use any kind of flip-flop. So register in the sense flip-flops in other names. So we will use one flip-flop for each state in a sequence. The output of a last stage is connected to the input of the first stage. In case of a ring counter, if we have the difference between any other counter and ring counter is the number of if you have an n-bit ring counter, which means that if you have 6-bit ring counter, you will have to cycle through 6 different states. There is no need for any decoding circuit here because the truth table will look something like this. Because only if you understand the truth table, you can understand the logic here. Say for example, this is a 6-bit ring counter. So your outputs will be, you will require 6 flip-flops. So your outputs will be from Q0, Q1, Q2, Q3, Q5 because you are going to use 6 flip-flops. Initially, when your clock is 0, your Q0 will be 1. When your clock is 1, your Q1 will be 1. When your clock is 2, your Q2 will be 1. Likewise, this will be 1 here. This is the function of a ring counter is. So this is the state diagram of a ring counter 1 0 0 0, and then the next will be 0 1 0 0 likewise. We have already seen what is the advantage of a ring counter is. What is the advantage of a ring counter? The advantage of a ring counter is only one output is active at any instant of time. So there is the possibility of overlapping or the possibility of getting an erroneous output is very, very less in case of a ring counters. But the disadvantage of a ring counter is they will use complex circuit. I mean, the cost will always be high because you are using large number of flip-flops. And the logic of implementation of a mod 6 ring counter is simple. How is the mod 6? We will be using D flip-flops only because there is no toggling of states that is taking place here. So we are not going to use T flip-flop. If we are not using T flip-flop, then we will not be using JK flip-flop also, right? So in case of ring counter, we will be using D flip-flops in the sense indirectly, and SR flip-flop indirectly a shift register, right? we will be using shift registers, and we have already seen that registers will be normally implemented using D flip-flop. Hence, this particular statement we used that we will basically registers are used as counters as these ring counters. In fact, to be more specific, as ring counters. Okay. Now, the logic behind in implementing. It's a very simple logic. This is the first flip-flop, second flip-flop, third, fourth, fifth, and sixth flip-flop. The Q0 output is fed directly to the D input. Q1 output is directly fed to the third D input likewise. And then the last output is again fed back and fed to the D0 input. And the clear signal, obviously it is there, and clock is fed synchronously to all the outputs. You see here, the clock is fed synchronously to all the inputs of your D flip-flop. Okay, and very simple implementation. This is how a mod 6 ring counter is implemented. Next we have Johnson counter, or the other name of it. Is important that you understand the other names also, because any name will be given for your exam. What is a Johnson counter? The other name is called as a twisted ring counter, or it is called as a switch tail ring counter or Mobius counter. So these are different names. How they are different is, in these counters, the complement of the output of a last stage is connected to the input of a first stage, which means, which is the last stage here? This is the last stage. This is the last stage here, right? And this is the complemented output of a last stage. And this last stage is fed as an input to the first stage like this. Then how will our sequence will change? And what will be our counting sequence is, okay. Before coming back to that, we will look at the circuit and then we will come back. So these are also called as twisted ring. It is a ring counter only indirectly, but it is a twisted ring. Our last complemented output is fed as an input. And the advantage with these Johnson counters is, though these are ring counters, this will require less number of flip-flops than your actual ring counters. Obviously, right? But this is the disadvantage with the ring counter. We are using a large number of hardware, large number of flip-flops. We have to reduce this. Hence, Johnson found out another logic. Hence, this is called as a Johnson counters. If you have n-bit Johnson counter, then it will cycle through 2 times n states. You have 4-bit counter, 4-bit Johnson counter, then you can cycle through 8 different states. So what is that we have done? We have reduced our number of flip-flops that we require in a ring counter by half. In case of a ring counter, if there are 8, if it is an 8-bit ring counter, then you will require 8 flip-flops. But here you will require only 4 flip-flops. So this is an example of a 4-bit. 4-bit means I will require, I can count till mod 8. Johnson counter. So everything is the same. The ring counter's logic only, that is A is fed, B is fed, C is fed, and instead of D here, it is D bar is fed back. If D bar is fed back, then what will be our logic? What will be our logic is, you see here, this is how your Johnson counter is going to work. It will first count 0, 0, 0. Okay, right? 0 clock cycle. Everything is reset here. During this clock, everything is reset. During the first clock, your LSB will get 1. During the second clock, your 2 inputs are fed, the last 2 inputs. Your third clock, 4 inputs are fed. And during your fourth clock, all the inputs are fed with 1, 1, 1. Now comes this complemented logic. Now, since, please remember that everything is 1, 1, 1 and 1 here. Now, since we are feeding a complemented input here, we are feeding 0 to our input here, right? So at fifth clock cycle, we are feeding 0. What will happen if we feed 0 here to our D flip-flop? Now this will become 0. In the next clock cycle, this will become 0. Now, the counting sequence, after 1111, it will be 0111. And the next clock cycle 0011 and then 0001. Right? So, after 8th clock cycle, but still we are able to count from 0 to 8. But only thing is the binary bits are slightly different. So what is the decoding logic here? What is the decoding logic here is, it is slightly difficult. So I think we will continue the next class. Still, let me see if I touch upon this. Yeah. Okay, we will complete. Okay. Now, what is the decoding logic? These are the clock cycles, and these are the corresponding ABCD outputs. 0000, and there are multiple decoding logics. If you consider, I can have A bar, B bar, A bar, C bar, A bar, D bar, likewise. Okay. All right. Now when it is 1, what is the logic that we can follow is, you can follow A and B bar. For 2, we can follow B and C bar, because we want to find the transition only. We are looking at the decoding logic only with 2 variables. So this is A and B bar, because anyway the C bar and D bar are already 0 in the previous case also. Only the transition is taking place from between A and B. So we have to combine the first 2 bits. Here we have to look only this logic, which is B C bar. Here the combining logic is C D bar here. Next logic is, there you cannot have a combination. So you can either have the normal logic will be, because the next change will take place between A and D only, right? So A and D will be your logic. So hence AD is taken. You can also take either AB, BC or DD, AD. Anything is possible. Next logic here will be A bar B. Then it is B bar C. Then it is C bar D. Then again it will reset to 0, 0. Hence you have to consider, because this 1 is going to change. So we are considering A bar and D bar. So, and there are multiple logics are also possible. So, so that is why you see here that I have already highlighted that we look at the extreme 2 flip-flops only. We will look at this flip-flop and this flip-flop. We will look at this flip-flop and this flip-flop, right? Hence the logic is, we will use A bar D bar logic or A D as our logic to reset. So yeah, so whenever we come across A bar, D bar or C bar, we will reach our state 0. Whenever we are having C bar and D, we will reach our state 7th state. Okay, whenever we are having the C bar D logic, we will reach our 7th state. So this is how we design a mod 8 Johnson counter. The logic circuit for a mod 8 counter, how do we reset? Because this particular decoding logic is used for resetting. If you want to say for have mod 6 counter, then what you do, we want only till mod 6, right? Mod 6 in the sense from 0 to 5 we are going to count here. We have to reset our Johnson flip-flop once we reach 5. So if you implement this A bar B logic, then you can use a counter. Though this is a 4-bit counter, you can count till mod 6 also. So that is the advantage, that is the logic behind this Johnson counters. Any doubt? I think. Any doubt? Okay. So with this, actually, we are completing our syllabus. As I said, that the PROMs, PLAs and PALs, we will cover only if I'm able to go to the campus. I mean, last 2 times I was not given permission to come to the campus, because teaching we can do it at home also. So hence, officially we are completing our syllabus today. Okay, I'm sorry. Officially we are completing our syllabus today, and we will use. I'm sorry, Deepika. I didn't notice this because. Okay. Though this is recorded, please go through it. Yeah.